Here we now move to a different topic, cloud applications and research. And if we look at the way scientific research is supported, we have large-scale supercomputers. Um, Blue Waters is one at Illinois. Texas has Stampede. Sequoia is the world, I think, the fastest supercomputer in the US. There just was one announced in China, and which is the fastest in the world, the so-called #1 in the top 500. It uses a new Intel chip to get very high performance. So we have supercomputers. These are single machines, maybe 1,000,000 cores, and they're designed to get optimal performance by assigning multiple cores or multiple nodes to a single job. Then we have so-called high throughput systems. Those are illustrated by the so-called Open Science Grid in the US or the European Grid Initiative. That's actually what's used in the Large Hadron Collider data analysis, because in that application, every event or every group of events could be analyzed on a different machine. And so you do not need a very closely coupled individual computer. You just need bunches of computers. In this case, you have LHC, there are computers across the world, which together analyze data. Then we need to try to take all these distributed resources and integrate them together. That's what grid technology does. And to do this, we use actually the same idea from cloud, software as a service, which is capturing the capability as a service, which a service is something that accepts data as input and gives you information as output. So a service is part of the DIKW pipeline, and it just enables that pipeline. A lot of services do. Then we have portals to access the whole system, and workflows that integrate services together into a single job. So if we look at the various ways of doing this, one way of measuring this is communication performance, because we're doing parallel computing and linking things together. Then we'll find the grids are the slowest because their machines are very distributed. That may not matter in the case of things like the Large Hadron Collider. All you need is to transport the data to the site it's going to be analyzed, and then it can be analyzed. It doesn't need to be linked closely with the other analyses, so grids are just fine for that problem. Clouds have better communication and synchronization performance than grids, but a classic supercomputer has the best synchronization and the best communication because they tend to be solving closely coupled problems where the different parts of the problem need to have high performance. So clouds can clearly execute effectively grid workloads, but they don't always access good supercomputer applications because they do not naturally support closely coupled applications. Virtualization, both in principle, if you virtualize, you're not quite certain what's next to what, so you don't necessarily get good communication. Also, hypervisors tend to produce overheads. So if you look at supercomputers, they offer the highest performance on closely coupled problems. And we can use a generalization of the concept of MapReduce to define 4 forms of MapReduce. The so-called map-only application, that's the Large Hadron Collider, everything is run independently. Classic MapReduce, that's as in, say, recommender engines, or which uses technology like Hadoop. That's a single map followed by a reduction, and then everything is written to disk for fault tolerance. Then we have so-called iterative MapReduce. This is running in parallel applications which are iterative and have multiple steps. Things like k-means clustering forms is of that form. And finally, we have classic MPI, where we're running not only closely coupled but also a lot of point-to-point communications, because in classic scientific simulations, you do not have large-scale communications. In the case of data analysis, the typical communication is large-scale. That's a so-called collective, reduce, scatter, gather, multicast, broadcast. And MPI is typically point-to-point, and those messages are much smaller, and you need special optimization to perform well. So it's very well understood, in my opinion, what works well when. And everything, a well-designed system has these different capabilities. And really, you have to decide, you look at your job mix and decide what you want to support what you're doing. And there is no single solution. Namely, if you put supercomputers everywhere, everything will probably run, or but they will run less. They will, and for some problems, they will run efficiently. And for data-intensive problems, they might not, because supercomputers tend not to have disks on every node, at least not large disks on every node, and so they don't run some of the so-called data-intensive problems which are present, say, for search and recommender systems so fast. If you look at clouds, there's not a lot of science use of clouds, that's what it says here, but I expect it to gradually increase. Science doesn't work at the timescale of industry. We don't have enough money to move as fast as industry. Industry is fighting to the death in new areas, and so they pour huge resources. And so if we look at what does work well on clouds, the long tail of science is particularly suitable for clouds. Sensors are particularly suitable for clouds. These are so-called pleasingly parallel applications with roughly independent data or sets of independent simulations. Data analytics appears to be very effectively making use of MapReduce or its iterative variants. And one example of a successful project is Venus C. It's a finished project in Europe, which was using Microsoft Azure. They had 27 applications that successfully ran on Azure. If we look at all the applications running on a system called FutureGrid, which is a public cloud run by NSF, half of those are from life science, which points out that when you have a new field like life sciences, it will use clouds more often than the more traditional fields where they have their codes running well on supercomputers and will not necessarily want to move to clouds. Locally, for instance, Lilly is a big corporation in Indiana. They are a big commercial cloud user for drug discovery. And they probably use those clouds more than the biology and chemistry departments at Indiana University. So here's a little more detail on this so-called parallelism over users and usages with the long tail of science. And I've already told you why the long tail is important. Big science is big telescopes and big accelerators, large experimental groups. In the area of things like genomics, environmental science, then you have lots of sensors run by individual scientists. They all gather data in a distributed fashion. It's worth noticing those fields, the data is intrinsically distributed. It's not like some where all the data starts up at the same place. If you go to genomics or environmental science, that data is taken from sensors which are scattered across the world. And then you would tend to centralize them into clouds, which would allow you to link data from different people together and provide this cost-effective computing. Sensors are more precisely thought of as the Internet of Things. These are all the little devices we put on the Internet. As usual, you'll get different answers to the number and different, depend where you go. But one number that seems reasonable is 24 billion devices by 2020. And that's a lot of devices. And all those devices are naturally supported by clouds because clouds are particularly good for lots of small devices, because every one of those small devices can instantiate a core on the cloud, and that core can be devoted to that, or if it's a very small device, multiple small devices. And so clouds are particularly suitable for lots of small things. They're not so easy to make use, actually, for one big thing which needs to be coordinated. And even the Large Hadron Collider is really lots of small things, because every time the LHC runs, each of those events that writes the disk can be thought of as an independent entity. So robotics is an important area. Driver cars, which are computer-controlled cars, are a particularly good example here. So in the Internet of Things, we have parallelism over things, and those things are distributed and they form a grid, as I mentioned. So grids are very important for understanding how to cope with distributed data. Here's an example of some sensors. We have a Microsoft Kinect, a smartphone, a Lego robot, a webcam. Here we have a sense of these three here are all connected to our work with Kansas on ice sheet dynamics, where we're looking at interfaces between snow and ice and using radar to determine that. So here we have what I call sensors as a service. These devices send their data back to a cloud, where that cloud then runs various software, which could in fact use MapReduce to coordinate the data and integrate it together to get a final answer. Like for this data here, we just need to know if the glacier will melt or how fast it's melting. And that requires integrated simulations taking lots of different data sets together to produce an answer. Here's a picture from Google of their car, which has obviously lots of sensors. Here's some probably video camera, I assume, and it's taking data from these sensors and making hopefully good decisions about where it can drive. Another good example of sensors. We have data on sports. We have search and rescue, and we have GPS-enabled photos. I told you there are 500 million photos uploaded every day. Some of those are pictures of your friends, but hopefully some of those are pictures of your of the agriculture and enabling us to detect disease by building a mosaic of all the photos uploaded across the country. That particular case is particularly important to have GPS enabled so that we can join lots of different photos together to produce a complete picture of whatever's going on. Here's an example of various scanning things here. We have, obviously, here's your thing that you can now scan, of course, at airports. You're using your mobile phone. And of course, the same scanning will allow you to hopefully even look up on the web how nutritious or your particular food product is. So this type of QR codes and their scanning are particularly interesting development, which is expected to get more important.